Okay, so it's 5 o'clock. We will wait 2 minutes for some people to show up, and then we will start. Okay. Okay, so we will get started right now. So hi everyone, welcome back. Good to see you after a day. So this is our second meeting of Intro to Calculus, and the topic today will be limits. So I will just share my screen. Share my slideshow. Okay. So this presentation will be on limits, and yeah, so this is the second class. Okay. So consider this function right here. This is called this function. We'll just say, let's assume it's x squared minus 2x minus 3 all over x minus 3. So we can factor the numerator as x plus 1 times x minus 3. And then we can split this up into two cases, right? We can make this a piecewise function. So the first case, when x isn't equal to 3, well, then we can cancel the x minus 3's out, and the function turns into x plus 1. But when x is equal to 3, then x minus 3 right here is equal to 0. And we have x plus 1 times 0 over 0. That's 0 over 0, right? So when x equals 3, this function is undefined. And here is the graph of this function. So you can see that it actually does behave like a line, x plus 1. And it only stops behaving like this line at one point, at x equals 3, when it's undefined. And so the question that we're asking ourselves is, how do we quantify this function? No, okay. How do we quantify this function at x equals 3? And so this is a very good question to ask. It's a natural question to ask. And you'll notice that as the input approaches 3, the output, the actual function itself, approaches 4, right? And this makes sense because if you plug 3 into x plus 1, you would actually get 4.
Medi Q is in the thing class.
Wait, can you please repeat that?
Nothing.
Okay. Okay. I'm gonna pin myself. Okay. So as x gets closer and closer to 4, the function seems to get closer and closer. So as x gets closer and closer to 3, the function seems to get closer and closer to 4. And the way we represent this mathematically is we say the limit as x approaches 3 of the function is equal to 4. I don't know if I'm not hearing something, but I think I hear someone unmuting. Can you please stay muted unless you have a question? Okay, thank you. So the limit as x approaches 3 of f of x in this case is equal to 4. And this is because, once again, as x gets closer and closer to 3, this function gets closer and closer to 4. So this right here, this LIM just means limit, and x approaches 3 of f of x is equal to 4. This is the value of the function had it been defined at x equals 3. And this is important. We study these types of limits because we talked yesterday a lot about tiny changes, right? We talked about a tiny change in time, a tiny change in circumference, and well, now we actually have a framework. If we use limits, we can actually formalize those concepts, and that's really important when when we do higher level math. We want, well, to formalize the math that we're doing. So this is the building block for all of calculus, really. Okay, let's just practice. What's the limit as x approaches 1 of this function right here? So notice that in this case, the function is actually defined at x equals 1. In the previous case, it was not defined at x equals 3. So it doesn't matter. We can still calculate what y or what f of x approaches as x approaches 1. Even if the function is defined there, that doesn't change the fact that we are able to actually calculate this. So let's see. This line right here represents x equals 1. And we have inputs, right, that are moving closer and closer and closer. They're infinitely close to x equals 1. And we want to see what that does to the output. And we notice that as x gets closer and closer to 1, the function gets closer and closer to -1. So that is the limit as x approaches 1 of this function. Notice that the function itself is also defined at x equals 1, but we can still calculate the limit there. Okay, here's another function, and we want to know what the limit is as x approaches 1 of f of x. So notice that this function right here, it follows this nice smooth curve, all except at one point, x equals 1. So there's a tiny hole in the graph, and the actual value for which this function is defined is right here. So this function is defined everywhere. It's just not smooth, and well, it's not a smooth curve. So notice that as this tiny point that like deviates from the normal function, right? That only happens at that one point. It doesn't happen anywhere else, even if you're like really, really close to x equals 1, like even at x equals 1.0001, that is still on this curve right here and not this point right here. And so as x gets closer and closer to 1, but doesn't quite reach 1, the function becomes closer and closer to 0. So that is the limit. And this is true even though this function at 1 is, well, defined at -1. It's defined like this, but the limit is still 0 because this function gets closer and closer to 0 as x gets closer and closer to 1. So there's also a potential case where this approximation, this approaching concept might not be valid. And that's when from the left and from the right, you approach two different values. So for instance, here, this red arrow is approaching 1, and this black arrow is approaching 1/2. Right, they approach different values. So this limit is undefined. We can't calculate the limit because it doesn't exist. There's no single one value that this function approaches as x approaches 2. What we can say, though, is that the limit as x approaches 2 from the right side of f of x is equal to 1/2. So this function gets closer and closer and closer to 1/2 for instance, x is equal to 2.001 or x equals 2.00001, right? Whenever x is bigger than 2, it and like starts approaching 2, it gets closer to 1/2. On the other hand, you also have x approaching 2 from the negative side, and that approaches 1. Yes, question in the chat. The instantaneous velocity. Okay, so this is actually not this lesson, not today, but we will have like a whole huge chapter on derivatives, and in that chapter we will figure out instantaneous velocity and instantaneous rate of change. And I'm going to remove the pin. Okay, remove pin. Okay. So yeah. So this limit as x approaches 2 of f of x is undefined because, well, there is no single one value, but from the right and from the left, it does approach a value. Okay. So let's see, what else do we have? We have shifted limits. So you will definitely be familiar with the graph of this function. This is the function 1 over x. And this 1 over x function, it like has a lot of infinity stuff in it going on, right? So for instance, this red line right here is called an asymptote of that function. And an asymptote is basically a line that the function gets closer and closer to, but doesn't quite approach. This function will never be equal to 0. Like 1 over x can never be equal to 0. And this function, for instance, has another line on the x-axis, like this, right? That's another asymptote of the function. It's horizontal, but it's still an asymptote because the function approaches it. And so we notice that, again, we use this plus notation to denote from the right-hand side. We note that as x is on this branch of the curve and is slightly greater than 0, right, it's approaching positive infinity. And from the negative side, this function right here is approaching negative infinity. So those are also two concepts I want you to be familiar with. They will definitely come up a lot in this course. Infinity and negative infinity. Okay. And then also, we notice that as x gets really big, right, as x approaches positive infinity, the function gets closer to 0. And the same thing when x gets really small. So by the way, the value that x approaches when we calculate a limit does not have to be finite. It could be infinite, and we can still calculate the limit. Okay. So now we will actually get to some of the hardcore math that deals with limits. So we will start off with some limit properties. So firstly, notice that when we multiply a constant by the limit of a function as x approaches a, where a is some value, it doesn't have to be finite, it could be infinite, but we know that it's there. That is the same thing as the limit as x approaches that value of this function scaled up by that constant. So that kind of makes sense. If you just imagine a function, right, c times f of x is the same thing as c f of x, and this is basically saying the same thing, just with limits. Then here we have another limit property. So this states that as so the limit as x approaches a of f of x plus the limit as x approaches a of g of x is the same thing as the limit as x approaches a of f of x plus g of x. So this is called additivity. The limit is additive. And notice one more thing. So this a value right here has to be the same for both limits, right? Just like exponent rules, a lot of the exponent rules rely on the fact that the base of the exponent is the same for both of the exponents that we're dealing with. Well, here's kind of the same situation. We want the limits that we're dealing with to be the same. Okay. So not the limits that we're dealing with, the values that x is approaching to be the same. Okay, so just a quick visualization of the first property. So these two are quite basic. I will try to go over them pretty quickly. We have function h of x. G of x is 3 times h of x. We notice that 3 times the limit as x approaches 0 of h of x, which is 3 times 1, is the same thing as 3, which is the limit as x approaches 0 of g of x. So this is just a visualization of the first property, and we could come up with a similar visualization for the second one. Okay, so using the first two properties, these are the first two properties again. You can multiply limit by a constant, and you can add them together, so that you can also subtract them. So the limit as x approaches a of f of x minus the limit as x approaches a of g of x equals the limit as x approaches a of f of x minus g of x. So I will give you a couple of minutes to work that out by yourself. I will stop sharing my screen right now. And you can private message me in the chat if you come up with a solution. I'm going to leave that up. gonna leave that up. Okay, yeah, I will definitely explain the solution after after a couple of minutes. So maybe like 30 more seconds, I guess. If you have a solution, type it to me in the chat. Okay, so we will go over the solution right now. So notice that we can rewrite this side right here. We can treat this minus as a -1 factor, right? We can treat this as -1 times the limit of as x approaches a of g of x. And then by the first property that we covered, we can pull that -1 inside the limit because it's a constant. So we have this right here. And then by the second property, we can add those two together. Inside the limit, we can add f of x and minus g of x inside the limit. And then after some simplification, that just yields f of x minus g of x. So the whole derivation relies on the fact that we can write the minus as -1. Okay, so this is another property that is quite important in limits. Okay, so here are the two properties that we already covered. And then here are, I'm going to show 3 more that are also going to be really important when we're actually evaluating limits. So these will be this right here. So limits are, you can take the limit of one function as x approaches one value, multiplied by the limit of another function as x approaches the same value, and that's equal to the limit of that same value as x approaches that same value of the product of those two functions. And then we can also divide two functions by each other, right? Take the limit, and that will be equal to the limit of one function over the limit of the other function. And by the way, all of these properties, you need to have the two functions, right? The limits have to be as x is approaching the same value for both limits, right? You can't have x approaches a for this one and x approaches b for the other one. And then the final limit property that we will use is if you take a constant and raise it to the limit as x approaches a of f of x, that's the same thing as the limit as x approaches a of that same constant to the power of f of x. Okay, so these are the 5 basic limit rules, and we can derive virtually any other limit rule from these 5 rules. So there will be 2 problems in the homework where you will be asked to derive 2 other limit properties from these 5. Okay, so is everyone good on limit properties? Yes? No? Anyone have any other questions about like why we need limits or something like that? No? If you do, please call them out because I'm not going to be checking the private chat all the time. I can't see it on my screen. So yeah, if you have any questions, just say them now. No? Okay. So now we will actually get to evaluating these limits. So if we are given a function, how can we evaluate its limit as x approaches some input? So the first method is just direct substitution, right? If we have the limit as x approaches 1 of x plus 1, what we can do is we can, since x plus 1 is defined at x equals 1, and it's a smooth, like linear, not necessarily linear, but it's a smooth curve at x equals 1. And because it's defined and it's a smooth curve, we can just plug x equals 1 into x plus 1, and we get the answer is 2. So as long as it's defined and it's a smooth curve, we can just plug in x equals 1 into the function to get the limit. So for instance, this complicated function, right, the limit as x approaches 2 of sine of x minus 2 squared, right, it looks very weird, but we can still say that the limit as x approaches 2 of that function, right, notice that there's no place really where this is undefined, where this could be undefined. And because of this function right here, sine of x minus 2 squared, is defined, and it's a smooth curve at x equals 2. It's also defined in a smooth curve everywhere, but we want to focus on x equals 2. And so we can just plug it in, x equals 2 into the function to find the limit, and the answer is 0. So that's the majority of limits will fall in this category. You could just quickly evaluate them because the functions are defined and smooth. So there are also more complicated limits. So for instance, if we are asked to find the limit as x approaches 2 of 1 over x minus 2. And when we try direct substitution here, we get 1 over 2 minus 2, which is 1 over 0, and that's undefined. So when you get a limit of the form c over 0, right? So here c equals 1. C is a non-zero constant in this case. That means that there is an asymptote of that function at the point x equals 2. So for instance, if we graph this function here, we can notice that we could calculate the limit everywhere else, but at this particular point x equals 2, we can't. And the reason is that, well, there's an asymptote at x equals 2. This is really similar to basically the same as the 1 over x case that we talked about earlier. And also notice that the right-hand and left-hand limits are different. So the right-hand limit, when it's on this branch of the curve right here, when it's approaching from the positive 2 side, right, the limit is positive infinity. And then here, the limit is negative infinity. So those are the two right-hand and left-hand limits. And in this case, the limit is undefined, firstly because it's infinite, and secondly, because the two left-hand and right-hand limits are different. So the main takeaway is that when you have a limit of the form c over 0, where c is a non-zero constant, there's an asymptote. Then there are even more complicated limits, like this one. So, for instance, what if our task was to find the limit as x approaches 0 of 1 minus cosine of x over 2 times the sine of x squared? So if we try direct substitution on this one, what we find is that 1 minus cosine of 0 over 2 times sine of 0 squared is 0 over 0. Notice that in the last problem, we also had it over 0. But the constant c had to be non-zero. Here, the constant c is 0. So this isn't undefined. This is slightly different. This is indeterminate. Undefined means there is no limit, or even if there is a limit, it's infinite. Indeterminate means, okay, that might be true, but we don't know yet, and we need to dig further to see if there is a limit. And the reason why this is true, why there is that possibility that there might actually be a limit, is that, so at x equals 0, this function is undefined, but when we want to find limits, right, we want to find, we really care about values that are really close to the value that we're evaluating the limit at, right? We don't care about the actual point itself, because at every other single value, this function is defined. So we can actually find a limit here, potentially, right? So indeterminate is 0 over 0. That's one of the forms, indeterminate forms, and this means that a limit might exist. So when we encounter limits like this, we try to simplify algebraically. So here, when we see sine of x squared, we might want to simplify that as 1 minus cosine squared of x, right? And then 1 minus cosine squared, we can factor as 1 plus cosine x times 1 minus cosine x, right? It's just difference of squares. And then we can cancel out the 1 minus cosine of x and the other 1 minus cosine of x, right? And we get that this is the same thing as the limit of 2 times 1 plus cosine of x. And again, even though we can't really make the cancellation because 1 minus cosine of x is equal to 0 at x equals 0, still, we only care about values that are really, really close to 0 and not actually x equals 0. And for values really, really close to 0, we can actually make this cancellation. And so this is completely legitimate because this is a limit and not like the actual function. And so when we try to find the limit this way, we can just use direct substitution now. So if you do direct substitution, if you plug in x equals 0 here, you get 1/4. So that is, we can just use direct substitution on that. But the moral of the story is when you have limits in an indeterminate form, you really need to try to algebraically manipulate the expression and see if you can find, well, a simpler way to write the limit. Okay. So here's another problem that you might encounter. Find the limit as x approaches -3 of x plus 3 over the square root of x plus 7 minus 2. So this limit is also really tricky because when we try direct substitution, it doesn't work. We get 0/0. That's indeterminate again. So there might be a limit, we just don't know yet. So you might want to try to algebraically manipulate it. And so what we do is we multiply both the numerator and the denominator by the square root of x plus 7 plus 2. And what we get in the numerator as a result is x plus 3 times root x plus 7 plus 2. And then here, right, we just have radical conjugates. So we multiply this radical expression by its conjugate, and this simplifies really nicely to x plus 3. And the x plus 3's then cancel out. Again, we can do this because we don't actually care about the value at x equals -3. We care about values that are really close. And for values that are really close, we can make that cancellation. And so we get that this is the same thing as the limit as x approaches -3 of the square root of x plus 7 plus 2. And here we can just use direct substitution to get that the limit is equal to 4. So anyone have any questions? No questions. If you do, please ask them now. You can just say them out loud. Okay, no one has questions. Okay, that's good. So I will move on to the next example. And by the way, one more thing before I move on, you might find it suspicious that the x plus 3's happened to cancel out so conveniently. And that's actually not a coincidence, because had this numerator right here been x plus 5, we wouldn't have had an indeterminate form in the first place, because the numerator would have been not 0, but 2, for instance, right? If x plus 5 would have been in the numerator. And then we wouldn't have had to do this in the first place. We could have just said that this is an undefined form and we're done. But because this is x plus 3, because we have to do indeterminate form, these will cancel out really nicely. So whenever you have this type of expression, this method will always work. It's not just some happy coincidence that this happened. Okay? Okay, good. So one more example. This time, x isn't approaching 0 on some finite value, it's approaching positive infinity. So the question is, what happens to this function when it gets really big? So the function is 4x cubed plus 5x plus 6, and we divide that by 2x cubed plus 7x squared plus 1. So we can try substituting x equals infinity into this. You might wonder how that would work, but basically you just get infinity, right? Infinity over infinity in both the numerator and the denominator. And this, by the way, is another indeterminate form. So just like the 0/0 form, this does not mean that all hope is lost. Instead, it means that it might be lost, but there's still a chance that there might be a limit. And so what we can do here is we can say, okay, as x gets really, really big, these x cubed terms will by far shadow the 5x plus 6, overshadow the 5x plus 6 and the 7x squared plus 1 terms. Because, I don't know, for x equals a googol, x cubed is a googol times bigger than x squared. So in general, when we have limits as x approaches either positive or negative infinity of rational functions, so functions with polynomials in the numerator and the denominator, we only focus on the higher degree terms because those dominate both the numerator and the denominator. They grow the fastest. And so when x gets really big, we only really care about them. So this limit right here is the same thing as this, much easier to evaluate limit, 4x cubed over 2x cubed. And this is equal to 2. So because the x cubed cancel out and the 4 and the 2 cancel out. So this is in general how you calculate limits of rational functions. Again, this turned out very convenient because the x cubed was the highest degree term in both the numerator and the denominator. But as a general rule, if the highest degree term here is bigger than the highest degree term here, so if the exponent of the higher degree term here is bigger than the exponent of the highest degree term here, that means that the limit is 0, right? Because that means that the denominator grows much faster than the numerator. Likewise, if the numerator's higher degree term is bigger than the denominator's higher degree term, what happens is the numerator will grow much faster than the denominator. And in that case, when that happens infinitely many times, right, we get an infinite limit. So the only time we actually get a number for these kind of situations is when the highest degree terms of both of these polynomials in the numerator and denominator are the same. Okay. Yeah, so these three examples are just to demonstrate indeterminate form. So we can use identities, algebra, and we can focus on the highest degree terms. Then one more way to evaluate limits before we close off this lecture. So this is called the squeeze theorem, or I like more the sandwich theorem. So the theorem, this is the theorem statement. It says that if one function is wedged between two functions for all values of x, and if at some point the limit as x approaches a of one of those functions, so the lower bounding function, equals the limit as x approaches a of the higher bounding function, then the limit as x approaches a of the middle function must be equal to those two external limits. And this makes sense, really, because so here I have f of x, here I have h of x, and here I have g of x. So notice that f of x is wedged right in between h of x and g of x. So f of x is right in the middle. And also notice that right here, the upper bound and the lower bound intersect. And since the upper bound and lower bound intersect, the only way for the middle function to get through that kind of tight gap is to actually pass through the point where they intersect. Notice that we use limits here because one of the functions might not be defined at that point. And that's fine. As long as there's a limit, we can use this. So again, the function might not be defined, but there might be a limit. So that's the good part. So we can use limits to actually help us with this type of scenario. And this is usually called a sandwich theorem because you can think of the analogy that h of x is the top bread and g of x is the bottom crust of the bread, and then the f of x is the filling, right? Okay, so I will now recap evaluating limits and how we do this. So first, you try direct substitution. Direct substitution only works when the function whose limit at some point you are trying to evaluate is defined at that point and smooth at that point, right? It doesn't have any inconsistencies, I guess. So no like points that aren't on the general curve. And in that case, you can actually try direct substitution, and that will most of the case save you a lot of time. Then if that fails, you can get a limit that yields an asymptote, right? A limit of the form c over 0, where c is a non-negative constant. A non-zero constant. And when you get a limit like that, you try values close to the number, see if there's a different right-hand limit or left-hand limit, see if they both verge to positive infinity, both verge to negative infinity, or if they both asymptotically converge to different signs of infinity. So that's how you deal with asymptotes in limits. Basically, try out values close to that point. If you get an indeterminate form like 0 over 0 or infinity over infinity, you could try simplifying with trig identities, rationalizing, and so on. And once again, there are many indeterminate forms. There are actually a lot of them, and we will cover them more in depth later on in this course. But right now, an indeterminate form is something that you definitely know is not an asymptote and is definitely not finite. So that's an indeterminate form. And you can find two functions that bounds the function whose limit you are evaluating. Then you can use the sandwich theorem if those two functions happen to intersect at that point where you are trying to evaluate the other function. And by the way, one of the homework problems, we will use sandwich theorem on one of the homework problems to solve it. So that will be a very nice application to find the limit of sine of x over x. And be really careful with right-hand limits and left-hand limits. So they might not be equal. And in that case, the overall limit does not exist. It only exists when the left-hand side and the right-hand side approach the same value. Okay. So this is the end of the presentation for now. Does anyone have any questions? If you do, please say them right now. Nobody has any questions? Okay. So in that case, I will review. In that case, I will review some of the topics on Google Classroom. So in Google Classroom, like a post will automatically appear at 6 unless the Google Classroom malfunctions, which I think it will. But if it doesn't, then a post will appear at 6. And in that post will be the slides for the lecture and the homework problems. So the slides for the lecture, they are you can review them at any time. And then for the homework problems, so here's the thing, I won't grade any of the homework problems. You don't have to complete all of them, but you probably should, because you probably won't get anything out of this course if you just listen to lectures. You also have to practice calculus. And also, if you will do the homework problems, make sure to submit them by a week from now. So that's by June 30th, because after that, I won't look over anything really. Yeah, I won't look over the homework. I will be checking other homework stuff. So yeah, I will provide more information with the next post. Okay, so if anyone has any questions about the content, about anything else, please voice them now. Yes?
Wait, so quick question. So you say that we have homework after every class, but let's say we have class on next week on Friday, and the next class is Saturday. So does that mean that we have class, or we have homework for Saturday on Friday?
No, for a week from then. So the homework on Friday will be due next to the Friday after that. Yeah.
Oh, okay. Now I get it. Okay,
yeah,
thanks.
Yeah. Okay. Any other questions? No? Okay. So in that case, then that's it. That's all I have for today. Thank you so much for coming. Once again, this is a very important topic in calculus. Like, I can't stress this enough. Limits will be the foundation for everything we do. We will use them in integrals, derivatives, and so on. So yeah, thank you so much, and have a good day. Okay.
Thank you.
Bye. Thank you.
Yeah.
Thank you. Bye.
Thank you.
She's